All right, so in this case, just like the last case, but in this case we're dealing with a resistance that is proportional to the velocity squared. And it's important to know, I feel that I may not have emphasized it in the last one, that it's proportional to the square of the actual velocity, not the velocity in the horizontal direction or the velocity in the vertical direction. It's proportional to the actual velocity. So we have to make sure we, be careful about that. Now we've just, if you set it up with an angle of alpha to the horizontal, so there's the resistance. If I use trig again, so if we look at the resistance in the horizontal plane, then remember it is proportional to the velocity squared, and we're interested, so it's proportional to the velocity squared, and we're only interested in the x, the horizontal component. So that part of that is the cos alpha part. So we're taking cos alpha part of that negative kv squared, and in the vertical direction again I'm just taking the sine alpha part of that for the vertical direction. Now if you think about this one, if I separate that like this, you can see we know that v cos alpha is our x dot, so I can write that as negative kv x dot. So you can see we can only partially split this up because there's still a v. The v is still here. Same with this one. If I break this up, I've now got my y dot. So again, partially, we've still got a v. So we can't really do calculus with our quadratic drag here. All right. But anyway, they are the components, the horizontal and the vertical components. Also, if we again used vectors to split these up, we've got minus kv squared. This is a little more involved. Remember that the velocity vector, if we think about it, we can take the size, the magnitude of it, and then times it by the unit vector. So v squared is just the unit vector times the v squared magnitude. In doing that, and remembering that v squared is just v dot v, it's a scalar product, of course. Our actual vector v, our unit vector, well, our vector v, we know, is x dot, so the velocity is x dot in the horizontal direction and y dot in the vertical direction, but that's the vector. We have to make it a unit vector, so we divide by the x dot, square root of x dot squared plus y dot squared. There we go. So here we've got negative k v dot v. Now v dot v, you know, is, if you think of the velocity vector as in that form, then v dot v, we would be doing x1 squared and then plus y dot. I say dot, did I say dot or one? Sorry, dot, yes. X dot squared plus y dot squared, and we are still timesing it by here. Now we've got x dot I plus y dot, sorry, this is not working very well, the pen. And here, so if I think of this, this is at x dot squared as well, and y dot squared, but it's in a square root, so it's to the power of a half. And this is to the power of 1. So if I put those bits together, I've got minus k, I've got 1 divided by half, so 1 take away half is half. So I'm going to have, I'll just put in a square root, x dot squared plus y dot squared. And then I've got left this x dot I plus y dot I, j, sorry, that's not great. And if I split that up, so we know this is just minus k. Now the square root of x dot squared plus y dot squared is just the velocity vector, v. And so I've still got x dot in the horizontal, y dot in the vertical. So again, splitting those up into horizontal and vertical components, There's my horizontal component, oops, minus kv y dot j. So there's my horizontal component, there's my vertical component. You can't see my dots, which is the same as these two here. So you can see it's not completely separated because there's still a V going on there. So this quadratic drag and its horizontal and vertical component still involves a V, so it's much more difficult to deal with.